going to work on chapter 17.5. So what we do here is use the same method of derivation that we use in chapter 17.3, using which we related velocity of two arbitrary points A and B on the rigid body together. We showed that velocity of point A is velocity of B plus omega cross r of A with respect to B, correct? So exactly that's what we have done. And we're gonna do a similar analysis here. And basically what we are doing, it's going to be taking a derivative from that equation. So here is what we had, and if you remember, for general velocity formula, we had VA was VB plus omega cross r of A with respect to B. And now we can take a time derivative from this equation, and let's make it a little thinner. If we do it, then we're going to get A of A is equal to A of B plus time derivative of here, this cross product. And since it's a cross product, it's two vectors product, we have to apply the product method. So it is going to be derivative of omega cross the second one, and derivative of omega, you know, it is called alpha. So alpha cross r of A with respect to B, and then plus omega cross derivative of r of A with respect to B over time, right? And if you remember, last time we have seen that, you remember last time we saw that the derivative of r of A with respect to B was equal to omega cross this vector, right? Because this vector has a constant magnitude. It only changes with respect to time due to rotating with angular velocity omega. So last time we used this, right? When we described the theorem, and then we used this one. Now we can do it again here. So if we bring it down, then we're gonna get our important equation that A of A is A of B plus alpha cross r of A with respect to B, and plus omega cross r of A with respect to B. So this is our big important formula for acceleration analysis. And this one says that if you have acceleration of one point, you need to add two terms to it to find the acceleration of the other point. One is this term, alpha cross r of A with respect to B, which if you remember from the past, this term, we know it as what? Tangential acceleration relative. And the other term is omega cross r, which we know this term as normal acceleration. And if the problem is a simple 2D problem, like the one we are dealing with right now, then I can show you that r of AB in this case is in the plane and omega is out of the plane, so they are perpendicular. Therefore, this term here can be simplified to magnitude omega squared times r of A with respect to B, which is what you see here. Okay, this is what you can see over there, that this this normal acceleration has a magnitude of omega squared r of a with respect to b, and this negative would tell you the direction. Because r of a with respect to b is from b to a, this normal acceleration is from a to b. And this is your tangential acceleration. So nothing new really. This is what we had in the past too, except in the past when we had pure rotation about a fixed point, we didn't have a of b, right? So if the object does not rotate, it goes through pure translation. What happens? Omega and alpha are both 0. You get a of a equals what? A of b, which is the definition of translation. Acceleration of all points are the same. If, on the other hand, object rotates about point b, so b is a permanent fixed point, so a of b is going to be 0, then a of a is going to be the tangential term plus the normal term, which we had back in chapter 13. Now that it is general motion, you basically add both of them together. So nothing new. So the two important formulas that we have learned so far is one, this one on the top for velocity analysis, and the other one in the bottom red box for acceleration analysis. Now we have used the top one quite a bit, so now it's time to practice on the bottom one, but we have to note one super important thing. When you want to do acceleration analysis, which means finding values of a or alpha, right? A and alpha are acceleration terms, whether linear or angular. Not only you need to know this vector r of a with respect to b, you also need to know what? Omega. And if you don't know the omega of the objects, finding a's or alphas cannot be done. So what do you need to do before doing acceleration analysis? You are right, we have to first do velocity analysis. We have to know all the omega values, otherwise it's not going to be possible. So here I'm going to add this important note for you, or you probably can see it in my lecture notes too. Let's see if I have added that. Yes. So whenever you want to do acceleration analysis, beforehand you have to have done velocity analysis. First velocity, then acceleration analysis. Okay, good. So now I want you to work with me through this interesting example of the object rolling on a surface without slipping, right? This problem we have analyzed in the past. The velocity analysis of it we have done. So we're going to do acceleration analysis. But I want to remind you of what we have done last time. So this is the problem. And here, I assume that this disk is rolling without slipping with angular velocity omega and angular acceleration alpha both counterclockwise. The radius is equal to r. I call the center point point B, and let's call this contact point point C. Okay. Oh, wrong. Sorry. C, and remember the radius was r. So if you remember, last time we found that velocity of point B, this is what we found in velocity analysis. So in the velocity analysis, if you remember, we found that V of the centroid is negative omega r times I. And we found that V of point C is equal to 0, if you remember, right? This is what we have achieved last time. And here when we say I and J, we clearly mean the traditional x and y axis, right? So this is to be your x and this is to be your y. And z to be out of the plane toward the observer. Good. So now we want to do acceleration analysis. And my question for you is this. What is A of point B? And what is A of point C? And note that omega and alpha are both given, so we are not going to find them. We assume that they are given parameters. Okay, so let's get started on that. So how do I first find the acceleration of the centroid? So how did we find the velocity of it last time? If you remember, I showed you last time that the distance traveled by the centroid between two time points, delta s, was, use a different color and bring it here. So if this guy rotates an angle of theta, so basically when this guy rotates, this point C now comes here, becomes C prime, this one was B prime, and if you measure the angle of line BC with respect to a vertical line, this rotated angle here, we called it theta. If you remember last time, we have seen that delta S, the distance traveled by the centroid, is equal to r times theta. It came from the definition of angle theta in radians. And then we took a time derivative from this, and we found that the time derivative of delta S, and delta S is the displacement of centroid, so it is going to be V of the centroid. In magnitude, it was r times theta dot, which was omega. And now I encourage you to take one more time derivative from this, and you're going to find that magnitude of A of B is going to be what? R times omega dot, which is r alpha. So A of point B is r times alpha, and like V of B, it is to the left, so I can go ahead and directly answer the first question. A of the centroid is going to be negative r times alpha I. So this problem was rolling without slipping, right? That is the problem we are dealing right now. So I could find the velocity of the centroid just by taking time derivatives of the distance traveled. But now, what about the contact point? The question is the acceleration of the contact point also zero? Remember, velocity of it is zero at the moment. What about the acceleration of the contact point? Is that also zero? Well, let's find out. So here, I'm going to relate the acceleration of C to acceleration of one other point about which I know something, and the only thing I know is now about point B. So I relate point C to point B through the new formula that we just have learned. And here I can either say plus omega cross R of C with respect to B, or because in this case R, omega are perpendicular to each other, So these two vectors are perpendicular because it's a 2D case. I can also say this whole thing is equal to magnitude omega squared r of c with respect to b, okay? So because this is a simple 2D case, I can also say such a thing, which helps me avoid performing a couple of cross product, although in this case it's not really hard because omega is only omega times k, so it's not going to be that bad. Okay, let's see what we have. So a of b was negative r alpha I. Alpha itself is in the k direction, the same as omega, so this is going to be alpha k. Omega was omega k. And this r of c with respect to b, it is what? It connects b to c. It's this vector. We have seen this vector in the past. So you have to connect b to c. It's this vector, downward vector, right? This vector is r of c with respect to b, which clearly is negative r times j. Therefore, a of c is going to be negative r alpha I. Then you have k cross j, and you know k cross j is negative I, but you have another negative, so you're going to get positive r alpha I. And then you have negative magnitude omega squared r of cb, but r of cb has a negative in it, so you're going to get positive r omega squared j. And when these two would cancel, you only get r omega squared j. So the acceleration of the contact point is r omega squared times j. It is not equal to 0. It is equal to the centripetal term, r omega squared, and it is positive in the j direction. It is toward the center. Now, does that make any sense? So, does it make sense? That was the question. And it says the contact point, if you look at these two info together, is currently stationary, and the acceleration it has is upward. So what do you expect to happen when, let's consider a car. If a car is stationary and it has a forward acceleration, right, because you push on the accelerator, what would happen in the next time point? Correct. It is going to get a small forward velocity, right? Because acceleration is the rate of change of velocity. So if you started with 0 and your acceleration is positive, you expect your velocities to go bigger positive values. So if initially you started at 0, maybe next time point it is 0.1, 0.2, 0.5 meters per second positive. And when you get positive velocity, it means what? You go forward. Yes. So in this case, the direction is rotated 90 degrees. So you have a stationary point and it has an upward acceleration. So you expect that point C at the next time point has a small upward velocity and it moves upward. Do you think the contact point moves upward as it rolls forward? The whole disk rolls forward. What about the contact point? Does it move upward? Does that make sense? So what you need to do basically is to draw the disk in two positions that are extremely close to each other. Okay, very, very close. In other words, your time dt should go to 0, very small. And then draw point C on both of those disks and then compare, right? So I'll try to do such a thing for you, because that's the question I asked my students in class. And I said, hey, do you think it makes any sense that the contact point is going upward? And some said yes and some said no. So what do you think? So here, this is what I'm gonna do. I try to make them as close as possible. Of course, you cannot make it 100% on the top of each other because then you cannot see anything, but let's say something like this. Okay, so here the black is the original disk and the blue is when it moved a little bit. So on the black one, if I say this is the center of the black, then right below it I call this point, and if you see here it is actually not easy to see the contact point, but let's say this point here is the contact point, and then for the blue maybe this is the contact point. So the displacement between them is what you can see here, this gap, right? So if you don't mind, I would like to clean up that and use blue color here, and then use a blue point here also. So something like this. So this is B, this is B prime, the new location. This black point is C, but the blue point is not C prime, it's the new contact point. Actually, this object has rotated, so point C prime is gone where? I mean, this point that was here now has rotated a little bit. So if you connect directly from B prime to this new contact point, if you can draw a vertical line directly like this, and if we can do that, see, it's not super easy, you cannot even easily move it. Let's see. No, even the resolution here is not enough to move this, so let me forget about that and see if I can draw it myself, although I don't think I can, but I'll give it a shot. Yeah, I guess I can do it better than the line. So then point C with respect to this new ball, the new configuration, has moved. So I can say if this one here I have to avoid double lines because that's gonna make it messy. Oh, no. It is really hard to draw on computer. Sorry. Yes. So if this angle d theta is the small angle that the disk has rotated, now this point on the blue is C prime, correct? And if you compare the location of C and C prime, what do you see? If you can zoom in, you see C prime is almost above C. So yes, actually, if you focus on the point of contact for a small, very, very small rotation, you clearly see that point of contact is going upward. It doesn't mean that the disk leaves the surface, no, because other point on the disk would come and serve as the contact point, but I want you to see that these two things that we found, V of C0, A of C R omega squared J, they do actually make sense physically. And I guess they do. So now it's time to look at one other example, example 17.6, where you have the 4-bar linkage mechanism. and omega of the input link AB is 10 counterclockwise, alpha is 300 clockwise, and you are supposed to find alpha BC and alpha CD. So what we do, we're going to take a snapshot, then we are going to solve this problem like that. So here again I have a mechanism, and you know a mechanism has more than one member. Here I have 3 members, so I have to apply these formulas that I learned here. I have to apply them 3 times. One for AB, one for BC, one for CD. And this problem is asking me to find what? What is alpha BC? And what is alpha CD? And let's use a vector notation because we also care about their direction. So we know we have to find alphas, we have to do acceleration analysis, but we learn before doing acceleration analysis, first we have to do what? Velocity analysis. So I'm going to do velocity analysis for this problem here as well, although if you remember, we have seen the same guy here, right? We have seen this in our classroom here in example 17.4, but when we found omega BC and omega CD in this problem, we solved using the instantaneous method. We didn't use the general velocity formula. So maybe now that I do it, it's basically we have seen how to solve this problem in different ways. Okay, but the numbers we're going to find for omega BC and omega CD will be the same as what we found in the classroom. So I'm going to do it again. It does not matter. So first we start from the member we know something and move toward the members we don't know. So we start with AB. We know something about A, and we're going to go for B. So we say V of B is first. V of A plus omega of AB cross R of B with respect to A. And we know that V of A is 0. Omega AB is positive 10K. And R of A with respect to B, which is this vector, or B with respect to A, I'm sorry. R of B with respect to A has 2 units and it's upward, so it is 2J. So when you do that, you're going to get negative 20I. And negative means B would move to the left, which with this omega, clearly it does move to the left. Okay, so this is omega AB, right? And this is alpha AB. So I found V of B. Now I go to point C, and I go to member BC, and I say V of C is equal to V of B plus omega BC cross R of C with respect to B. And R of C with respect to B is this one. And V of B, I have it completely, so I write it down, negative 20I. Omega BC, I don't know, so let's say for the moment being, I also want to find omega BC and CD. Because I need them, so let's do it all. So omega BC, I have no idea. All I know is since this is a 2D problem, omega BC has to be either positive K or negative K. So I choose one of them and I say, well, I assume for the moment this is positive, so I make it to be omega BC K. And R of C with respect to B, you see, it's 2 units forward, so it is 2 times I. What do I know about V of C? Nothing. I don't know its magnitude, and I don't know. I can find something about its direction. We know C is rotating about D, so velocity of that should be perpendicular to CD. We can do that, but the other thing that I encourage you to do is, since we ultimately are not going to find VC, we don't care about it, I say, well, V of C can be found through member BC, but also V of C can be found through what? Member CD, right? Because C also belongs to member CD, so I can find its velocity through member CD. So the top one, if you simplified it, it was negative to any I, and then we have K cross I, right? Which is J, so it's going to be plus 2 omega BCJ. This one, D, is a fixed point, so the velocity of it is 0 omega CD. Again, I don't know its magnitude, so here I go ahead and assume that it is positive K. It might turn out to be negative, and R of C with respect to D connects D to C like this. This is R of C with respect to D, which is negative to I, positive to J. And if I carry the cross product, it's going to be K cross I, which is J, and then there is negative, so it is going to be negative 2 omega CD J, and then you have K cross J, which is negative I, and you have another negative, so you are going to get also negative 2 omega CDI. So I found V of C through both members, but I know these should be equal, right? Because they're both V of C, so if I call this equation 1 and if I call this equation 2, from 1 and 2, what do I conclude? The I components are equal and the J components are equal. Here the I is negative 2 any. Here the I is negative 2 omega CD. Here the J is 2 omega BC. Here it is negative 2 omega CD. So from here, clearly omega CD is going to be positive 10 radians per second. And positive means, yes, it was really K. And if you plug that now down here, you see that omega BC will turn out negative 10 radian per second. And negative means the direction that we considered initially was wrong. It is clockwise. Okay, so these are the two omegas that we needed. I got both of them, and I can write them somewhere. So now I would say, okay, so omega BC is negative 10K, and omega CD is positive 10K. Okay, I got my omegas. Now I can do acceleration analysis and go through alphas and A's because I have my omegas. So now let's do acceleration analysis. So now again, I relate my acceleration of, I start from member I know something about, which is alpha AB, and go to our members I don't know. So it's going to be acceleration B is equal to acceleration A plus alpha AB cross R of A with respect to R of B with respect to A. And again, since this is a 2D problem, I say negative magnitude omega AB squared R of B with respect to A. So the reason that I'm not doing the double cross product, again, remember, because this is a 2D problem. And then we say A is a fixed point. It doesn't have acceleration. Alpha AB is clearly 300, but it is clockwise, so it is negative 300k. Magnitude omega is simply, if I'm not mistaken, it should be 10, right? So it is 10 squared. And R of A with respect to B is what? We had it was 2J. So if you carry the cross product and simplify, you are going to get negative 200J, and then you have K cross J, which is negative I, but that is also negative, so you are going to get positive 600, right? So it is going to be 600I, and then minus 200J meters per second squared. This is A of point B. Does that make sense? It says it is to the right and downward. Is that correct? Well, we know B is rotating about the pinpoint, about the fixed point. Therefore, it has two acceleration, a tangential and a normal in general. The tangential determined by direction of alpha. Since alpha is clockwise, tangential 1. So this is going to be R A of A, B with respect to A tangential. And then the normal is always toward the center. So this is A of B with respect to A normal. And you see it is negative J and positive I. And this says yes, the A of B that I found is correct. Now I go to A of C. And I say A of C is equal to A of B plus, because A of B I just found. And C is an intersection point, so these are my candidate points. Plus alpha BC cross R of C with respect to B, and then minus omega BC squared R of C with respect to B. A of B, I just had it, 600I minus 200J. Alpha BC, I have no idea the magnitude of it, but I know because it's a 2D problem, it is either clockwise or counter, so I consider it to be positive, so I say it's alpha BC times K. Is that correct or not? We'll find out at the end. Magnitude was negative 10, but when you square it, it doesn't matter. It's going to be positive 100. And R of C with respect to B was 2I, right? If you go back and look at the picture. Good. So if you simplify this, you are going to get 600I minus 200J. And then here you have K cross I, right? Which is J, so you're going to get 2 alpha BC J, and then minus 200 I. Yes? So what do you know about A of C itself? Really nothing, because you don't know its magnitude. Its direction you can find, kind of, it's a combination of tangential and normal, but again, like the previous case of equations 1 and 2, I encourage you to Say A of C, I could find both using member BC, and now I can also find it using what? Member CD. So I say A of C is A of D plus alpha CD cross R of C with respect to D minus magnitude omega CD squared R of C with respect to D, and note that A of D is 0. Alpha CD is, I don't know, I just consider it to be positive K. It could be negative K, but it's either positive or negative K. Omega CD was positive 10 squared, and then R of C with respect to D was, if you remember, it was negative 2I plus 2J. So if you carry out the cross product, you would get K cross I, which is negative J, or K cross I is J, but you have a negative here, so it's going to be negative 2 alpha CDJ. Then you have K cross J, which is negative I, so you're going to get negative 2 alpha CDI. And then minus 100 times this, so this is going to be positive 200I and minus 200J. And now you call this one equation 3, and you call this one equation 4, and you say in 3 and 4, they're both A of C, so these two vectors have to be the same. So you say from 3 and 4, I have i's to be equal. What I do you have on the top one? You have 600 minus 200, so you have 400. Here, how many i's do you have? You have 200 minus 2 alpha CD. J on the top is negative 200 plus 2 alpha BC. And here it is negative 200 minus 2 alpha CD. So now if you solve this, clearly alpha CD, it is going to turn out negative 100 radians per second squared. And here if you solve for, this should be alpha. Let me fix this. This is alpha BC times positive 2, right? Which you had up there. You see alpha BC is going to be negative alpha CD, and it's going to be positive 100. And these are my alphas. Okay, so BC is 100, the other one is negative 100, and I can go and write them over there too. So this one was positive 100 K, and this one, the other one was negative 100 K, and of course 100 what? Radians per second squared. This is radians per second squared. Don't forget the units. And this is radian per second. And this is radian per second. So never forget the units, otherwise it's meaningless. There we go, problem solved. Now, let me tell you one super important thing. So, this is the thing. When this mechanism starts to rotate, right? This mechanism starts to rotate, so this member is going to go counterclockwise. This member BC is negative, so it goes clockwise. This guy is positive, it goes counterclockwise. So the mechanism changes shape, right? So let's say 1 moment from now, if this is the start of the mechanism, something like this, correct? So this is how the mechanism started. And now, 1 point after, you have something like this. Let's use a different color. So this member gone counterclockwise like this. This member gone counterclockwise like this. And this member gone clockwise like this. Okay, and let me make this a little shorter if I can. Okay, so the mechanism from the black configuration goes to the red configuration. And now the question is, all of these numbers that you found, right? 10, negative 10, 100, and so on and so forth, assuming that these two will not change, right? So that 10 and 300 still there. So you can still say that the red one is going with 10 radians per second omega and 300 of alpha. First, can you say that? The question is, can you say that? The answer is no, you cannot. Even if alpha is constant, which it could be if you can maintain it uniform, constant alpha with the motor. So even if this guy is constant, omega is going to change, right? Because you know, when alpha is constant, omega AB is going to be omega AB not the initial omega AB plus what? Alpha AB times T. So when T is non-zero, your omega AB will change from its initial value of 10 with the, do you think it's going to get bigger or smaller? Smaller, you're right? Let's say this is just 1/10 of a second. This is positive 10. This is negative 300. Okay, and let's make it even smaller. So let's say it's 0.01 second. Okay, just 10 milliseconds, a small number. What number would you get? This is 3, that is 10. You're going to get what? 7. So 10 milliseconds after you start the motion, now this guy is going to go to what? 7 radians per second. So here you have a camera that can capture 100 frames per second. So every 10 milliseconds you have 1 frame. So you're going to get this red configuration. So that is your omega, this is your alpha. Clearly your angles would change. The R of B with respect to A, C with respect to B, and C with respect to D are not simply 2i, 2j, and negative 2i plus 2j. Now you have some angles. So you have to calculate these angles and then find this unit vector. So you have to calculate this theta AB. How much is that? And then calculate this angle. If you continue these two, this angle is theta BC, and then this angle is theta CD. And then with these angles, with the initial angles they had, now you find the new unit vectors. The only thing that does not change are this length. This is 2, this is 2, and this is 2 square root 2. The length are not going to change, but the angles do. And you clearly can find the new theta AB. You can say theta AB is original theta AB, because alpha is constant, plus original omega AB times t plus 1/2 alpha AB times t squared. And so you plug in your numbers initially, depending on how you measure it. If you measure it with respect to the vertical line, then you can say this is 0. If you measure angles with respect to the horizontal line, then the original angle was 90 degrees. So let's say we are measuring them with respect to their original one. Let's say we measure them with respect to the x-axis. That's what we do always. So this is 90 degrees, pi over 2. This is positive 10. This is a millisecond. This is a millisecond squared. And alpha was negative 300. Right? So if you calculate, this number is going to be 0.1. That number is going to be negative 0.03. So you're going to get positive 0.07, so it is going to be pi over 2 plus positive 0.07 in radians. So this change here is 0.07 radians of theta AB, and then keep going. So the question is, if I want to calculate omega BC and omega CD in here, and then alpha BC and then alpha CD, what numbers do I get? Do I get the same numbers as I got last time? Absolutely not. All of these things that we do here, all of these equations, all of these solutions are only what? Momentary equations. They are only valid for that moment. So now that you have rotated even a little bit, your position vectors have rotated, so they are, in terms of ijk, they are different vectors now. Your omega of the input probably changed too, so all of these numbers have to be recalculated. Okay, so keep that in mind. Nothing here that you do in these equations, the general velocity formula or the general acceleration formula, always these calculations are what? Valid for a moment. So both of these equations are evaluated at only one time point. They are both momentarily valid or momentarily equations. Next time point, they are still valid, but the numbers are not going to be the same numbers. Okay, you have to be redone. You have to be redoing them. They have to be redone. So please keep that in mind.